So today we're going to talk a little bit about acids and bases, and in the upcoming, in the next few lessons, we're gonna be going in much finer detail about acids and bases. But for now, I just want you to give you guys a brief intro into how is it that we define acids and what is it and bases, right? So there are basically two models that we use to define base ac- acids and bases. So that the first one is the Arrhenius model, and the second one is the Lowry Bronstead model, right? Bronstead model. So both of them have their own specific definition on how is it that you should define or identify an acid or a base. So according to Arrhenius, an acid can be described as a substance that produces hydroxide, I'm lying, that produces hydrogen ions or hydronium ions when added in water. So it's right in water, right? And on the other hand, he describes a base as a substance that produces hydroxide ions. So it produces hydroxide ion OH ions when added in water. And I'm sure you can already pick up a slight limitation of this model because it requires either the acid or whatever the reaction to be occurring between the acid and water or between the base and water. What about instances when those reactions don't actually occur in water, right? So to kind of um, make up for that limit, we can now use a different model, which is the Lowry Bronstead model. And according to him, he says that an acid can be defined as a proton or H plus ion donor. So it donates a proton. And then a base, on the other instant, can be defined as just the opposite of this. It is a proton acceptor. So it will accept that proton that was donated by our acid. So proton, proton acceptor. But of course, we use both models, depending on the type of situation we have. So it's quite important for you to be able to distinguish between these two. But just speaking a little bit about the proton donation or proton acception, we can talk about different types of acids that or acids that may some acids, for example, will donate one proton, some will donate two, some will donate three. So for acid that will donate one proton, we there's a specific name for them and we say they are monoprotic. Mono means one, right? And for acids that actually donates two protons, we say they are diprotic. Di means two. And for acids that donates three protons or more than three protons, we can say it's triprotic. If acids donate two or more, sometimes two or more protons, you can sometimes call it a polyprotic, right? So it's quite essential for you to be able to know these differences, right? Cool. So next up, we actually just gonna get into when we have a reaction of acids with bases, and you'll see how those reactions actually occur. So let us take just a few examples of what Arrhenius was basically trying to explain. So remember, he said that an acid, when added in water, will essentially produce hydronium or hydrogen atoms. So an acid in water will simply this is an acid, is hydrochloric acid. It will sort of dissociate, split, and it will produce those H hydrogen ions plus your Cl minus. On the other hand, let's take an example of sodium hydroxide, which is a base, and then you add it in water. What will happen to it? You'll find that you'll dissociate into sodium plus hydroxide. So you realize a base in water, according to Arrhenius, will produce this OH. It will increase the concentration of hydroxide ions, and this one, an acid, for example, will increase the concentration of hydrogen ions, right? But now let's see in terms of Lowry-Bronstead model, what will happen. So remember, according to Lowry-Bronstead model, he said that an acid is a proton donor, and so let us have a reaction between hydrochloric acid. Let's write it properly. So we have HCl plus ammonia, NH3, and what do you think we will get as our product? And in that reaction, what you would get as your product is that you find that you have NH4 plus Cl minus. But how did this happen? Okay, so we can just try to break this reaction into two. We can say, all right, so HCl, right, which is an acid, will donate a proton. So that's the proton that it's going to donate, right? And ammonia, on the other hand, will accept a proton. So it will be this ammonia plus a proton, which will now give us NH4 plus, right? So HCl will donate this proton, and then in return, NH3 will accept that proton like that, and then essentially that's when you will have your HCl plus NH3. So remember, this proton that HCl donates is the proton that is accepted by NH3, meaning we will only be left with Cl minus plus NH4 plus, right? I hope that is making sense. So in this instant, meaning HCl, because it donated a proton, it must be an acid. And ammonia in this case, because it accepted a proton, it must be a base. I hope that is clear. Let us try to take another example. So let's say you had acetic acid, so CH3 COOH is acetic acid plus water, which will form hydronium ions H3O plus this CH3COO minus. So for this to be true, for acetic acid and water to form hydronium ions and CH3COO minus, what does it mean? It means that this must have donated a proton. So our acetic acid CH3COOH must have donated a proton. So a proton, this proton there was removed because it's going to donate it. And we are left with that minus there plus H plus, right? And for this water, remember we had water. For it to form H3, it means that it must have accepted a proton, such that we have H3O plus, right? Cool. So essentially that's when you have that reaction there. So this one donates the proton, and this proton essentially is accepted by water. So you have CH3 COOH plus the water, which will give us CH3COO minus plus H3O plus, right? So because this one donated the proton, it must be an acid according to the Lowry-Bronstead model. This one, because it accepted the proton, it must be a base, right? Let us take another example, and you're gonna notice something quite interesting. So let us take an example where we say, okay, let's us have ammonia and H3 again, and this reaction with water, right? And you notice that it will give us this ammonium ion NH4 plus hydroxide OH minus, right? Cool. So to be able to, for ammonia to be converted into this ammonium ion, it means that it must have accepted a proton. So you must have had NH3 plus a proton, which then yielded us. So if we add that there, you now have NH4 plus, right? And then for this water to now turn into OH, it means that it must have donated a proton. So meaning it donated this proton, yep, and then it got left with OH minus, right? So it's the same thing, you just add, you have NH3 plus H2O on this side. And this proton that is donated by this proton that is donated by water will be accepted by the NH3. So in this side, you're just left with NH. It's almost like they're canceling each other, right? If you look at it that way, NH4 plus OH minus. So ammonia on this side, it accepted a proton, so it's a base. Cool. And then what is this? Water donated a proton, so it is an acid. I don't know what are you noticing? You must be noticing something interesting here about water. In this reaction with acetic acid, water accepted a proton and we said it was a base. But in this reaction here, water actually donated this proton, and if you use the Bronstead model, it means that it is an acid. So what that must be telling you is that there are some substances that actually act as either a base or an acid depending on what it is reacting with. And there's a name for those types of substances. I'm trying to find where I can put this. So we normally call them a very specific name. We say they are amphoteric substances. So water is an example of those types of substances. They can either act as a base or an acid. So you find in one reaction they are bases, in another reaction they are what is it? They are acids, right? So it's not only water that behaves that way. You will also know that ammonia can also act as a base or a what is it? A base or an acid. We can also have zinc oxide. When I was doing my honors, I actually worked with this material of zinc oxide for solar cells. Or we can also have beryllium hydroxide. You can also try to find others. So these substances basically are amphoteric. It means that they can act either as bases or acids, right? Cool. So let us try to take just a last example. So let us say you're given an equation such as this one, H2SO4, a sulfuric acid, and then it reacts with water. So I'm already writing it in its balanced form, and it produces 2H3O plus plus this sulfate ions. And it's very important for you to include the state. I realize that I haven't been including this in my calculation. So this is aqueous, right? Cool. So, and then you are asked to now identify which one is an acid. Let's say you don't know that this is sulfuric acid, right? So how would you go about it? So we're gonna use the Bronstead model, right? So we can say, so we'll say, okay, this sulfuric acid, or let us start with water. So we'll say this water turned into hydronium ions. So it means water must have somehow accepted a proton, right? So this water must have somehow accepted proton. So we have 2H2O which will accept two two hydrogen protons, which will then give us 2H3O plus. So you just always make sure that the number of hydrogen, so it's 6, oxygen is 2. So just making sure that it's balanced. So it means that it's very important for you to be able to write balanced equation at this stage. You know, in metric now, so you should be able to do that with ease. So this means that this one is a base because it accepts those two protons. But where are these two protons coming from? This means that H2SO4 sulfuric acid will actually have to donate these two protons. So 2H plus so if we take those two protons from this, we'll just be left with SO4 2 minus because we've taken 2, right? And then now you see that, okay, this water accepts these two protons that are donated by sulfuric acid. So we have on the side that 2H2O plus H2SO4. On the other side of the equation, we are left with 2H3O plus that sulfate ion, right? Cool. So I'm hoping that is made it clear for you to be able to differentiate between acids and bases using either the Arrhenius model or the Bronstead model, right? Cool. So according to Arrhenius, acids, they will produce H plus or hydronium ions in water, and bases will produce hydroxide ions in water. We've already shown you how they do that when we took the example of HCl as well as sodium hydroxide. Laurie Bronstead says, in the other hand, an acid will donate protons, so it's a proton donor, and a base in turn will accept those protons, proton acceptor, right? So you should be able to just differentiate between that. So the last few things that we can talk about is the strength of a base or an acid slash base strength or relative strength, right? Oof, is that how you write this thing? Yeah, strength. So you know what I'm saying. So there are different types of acids and bases. There are acids that are, so you can have acids that are strong, and you can also have acids that are very weak, right? So how do we distinguish between the two? Strong acids are said to ionize completely in water. See, they ionize completely in water to produce high concentration of, so you will have a high concentration of either H plus or hydronium ions. Examples of strong acids that we normally come across in the lab, you have your HCl, hydrochloric acid. The other one is H2SO4, sulfuric acid. The other one is your nitric acid, HNO3. So these are very strong acids. When you're working with them in the lab, you have to be extremely careful because they are quite corrosive, right? So they can actually burn your skin. Cool. But we also have weak acids, like we mentioned. And how do we define weak acids? So we say weak acids, they are the opposite of this. They do not, so they ionize incompletely when added in water, and they form very low concentration of either hydrogen ions or hydronium ions, right? So this is very important for you. It's very important for you to be able to distinguish between strong, or to define what's the difference between a strong acid as well as a weak acid, right? So some examples of weak acids, we have acetic acid. So that's CH3COOH. So remember, this is the one that they use in vinegar. There's also another one, oxalic acid. So it's COO. No, there's an H here if I remember here. So this is oxalic acid, right? So I just want you to make you aware of something. I can't possibly cover all the acids or bases that are there. So it's quite important for you to just always visit your books and make sure that you know these acids, you know their names. Also, additionally, check your examination guidelines. It will give you a clear indication of which acid is it that you're supposed to know, as well as the bases, right? So now let us talk about the relative strength of bases. So additionally, we can talk about bases, right? Can talk about the strength of bases of a base, right? So we can have quite strong bases as well as weak bases. And you have to be able to kind of differentiate between the two. So strong bases are said to dissociate completely in water. Completely, right? Let me just wipe that and write it on the next line, right? So they dissociate completely in water. On the other hand, weak acid are said to dissociate incompletely. Dissociate or ionize incompletely in water, right? Cool. So these ones form very high concentration of hydroxide ions, high of OH, and this one form very low concentration of hydroxide. Right? An example of a strong acid that we can take is sodium hydroxide. It's a very strong acid, no, a strong base. I apologize. And then there's also potassium hydroxide, KOH. And then an example of a weak base. You have your ammonia, you have your calcium carbonate. There's also sodium sodium hydroxide. No, I'm lying. Sodium hydroxide is a strong base. So there are many others, right? There's also potassium carbonate. So just make it your task to make sure that you know most of these um, acids and bases. So another thing, just I'm trying to end this lesson, that is important for you to know, is whether an acid is concentrated or it is dilute. So I'm sure you've heard a lot about when you talk about, okay, this is a concentrated acid, or it is a concentrated or a dilute acid. So a concentrated acids or bases, they contain large amount of an acid or a base. So if we say something is a concentrated acid, it means in proportion to water, there's a lot of acid in there. If we say something is a concentrated base, so in proportion or in comparison to water, let me just make an example. So HCl plus H2O, if we add HCl in water. So if we have a lot of hydrochloric acid than water, it means that we will actually have a concentrated, a concentrated acid. However, if we have a more water than the acid, it means that we will have a dilute acid. So the same thing can also be described for what is this, for bases. If we have a lot of a large volume of the base in comparison to the water, we say it's a concentrated base. If we have a very small volume of, or whatever, acid, a very small acid in comparison to the water, we'll say that we have a dilute acid. So yeah, so choose This served as just an introduction to acids and bases. The next few lessons are still going to primarily focus on acids and bases.